So in this chapter, we'll do AC circuits. So what this means is, to a circuit, we'll connect an AC source, okay, an alternating current source. So let me show you how to produce alternating currents, okay. So here's a generator. So you need a permanent magnet. And then you take a wire, a coil of wire like this, and see this coil of wire is connected to this ring, and we have brush, it's connected to the outside, and it's connected there, and we have brush, it's connected to this load. That's the load. Now if you turn this coil, okay, what this load sees is an AC voltage like this. Okay. And if this wire is turned 100 times a second, you get a voltage whose frequency is 100 hertz. Okay. You can change the amplitude of this by increasing the area of this coil, by adding more turns to the coil, and so on, and then you can increase the amplitude. Okay. But the frequency at which you turn this coil is the frequency of the AC signal. And it's a sinusoidal signal, okay, voltage that you produce. Okay, so what this device is doing is it's converting mechanical energy. You're putting in mechanical energy in when you're turning this thing, you have to do work to turn this coil, and that is being converted to electrical energy. Okay, so this is a generator. It's a generator converting mechanical energy to electrical energy. Okay. How do you turn this coil?
With water, wind.
Yep. In a dam, the flowing water turns that. In a windmill, the wind is turning the blades, which is ultimately turning this. In a nuclear power plant, you split nuclei from the heat, you boil water, and the steam turns it. In a thermal power plant, you burn coal, boil water, the steam turns it. Okay? So this generator converts mechanical energy to electrical energy. Why are we converting all different kinds of energies to electrical energy?
To power homes?
Well, so I could send a bucket of coal to your home, and then you use the coal.
Electrical energy is more efficient.
So it's easier to transport electrical energy over long distances, and it is more efficient. Okay? So that's why we convert all kinds of energies to electrical energy. Okay? You can't bring a flowing river to your house. Okay? So there are only certain locations that are good for hydropower. You convert that to electricity and then bring it into your homes. Okay. So the angular frequency of the EMF is equal to the angular speed of the loop. Okay. So the frequency of this voltage output is equal to the frequency of this loop. Okay. So this is the source we are going to connect to your circuit. Okay. So here's an AC source. There's the amplitude of the voltage. Okay. So for instance, what do you get out of the wall socket? What are you getting out of the wall socket? How many volts are you getting? I'm sorry? 120 volts. Okay. That 120 is what we call a VRMS, which is V max divided by root 2. Okay. So actually the amplitude of the voltage is about 170 volts, what you're getting out of the socket. Okay. All right, so this is the voltage you're getting. Okay, and we're going to hook this source to various things. So you plug in your light bulb and you plug in your refrigerator and all that kind of stuff to the wall source. Okay, so you're going to plug to these AC source. Okay. All right, here's what this chapter is about. So you're going to connect this device to your AC source. Okay. And these are the two things you want to know. Okay. So this is the AC source you've connected. And what you want to know is what is the current that is being drawn. And look at here are two things about the current. You want to know the amplitude of the current, okay? And you want to know this thing called the phase factor. So those are the two things you want to know. Now let me remind you of, let's do a DC circuit, okay? So here's a battery, and here's a resistance, okay? Voltage, resistance. What was the current in this circuit? You guys remember?
V over R?
V over R, very good. V over R, okay? So the amplitude of the current or the magnitude of the current is the voltage amplitude divided by the resistance. Okay, so you can think of this, the current as E max, that's the EMF, maximum EMF. And the generalized term for resistance is impedance. Okay? Sine omega t minus phi. So, what we are interested in is for a given circuit, there are two things we're interested in. Z, what is Z of the circuit? What is the impedance of the circuit? The resistance of the circuit. Okay? And we are interested in phi. So these are the two questions that we want to know. Okay? The impedance tells you the higher the impedance, lower the current. Okay? And, the power dissipated, if you remember, the power dissipated in this circuit is I square R. And so lower the current, lower the power dissipated. Okay? So higher the impedance, lower the power. Okay? And this is a very important factor in AC circuits. So you will learn toward the end of the chapter that if this guy, so this is a number, phi can take values between pi by 2 and negative pi by 2. Okay. So what you learn is when phi is 0, that's when this circuit is doing something. That's when it's cooking. It's cooking at maximum power. So you want to remember that. When phi is either plus or minus pi by 2, you're not cooking anything. There's no power dissipated in this circuit. All that is happening is energy is being sent there and then sent right back in the next cycle. All right, so I'm going to state it now. Maybe you might not understand this, but if this is Hoover Dam and this is your city, and if phi for your city is plus or minus pi by 2, no lights are burning in your city. Okay? So what you want for your city is for phi to be 0, for maximum power to be delivered. Okay, so this is absolutely amazing. If this is your city, for maximum power to be delivered, phi has to be 0. This could be your radio, and instead of Hoover Dam, how is your radio getting energy?
Batteries?
Through electromagnetic waves. It's getting information through electromagnetic waves. That's sort of an AC source. And if phi for your radio is 0, that's when it's gathering maximum power. That's when it's tuned to that frequency. All right, so again, let's back up a second. Okay. So I'm going to erase some of this stuff. Okay, so we are going to connect an AC source to our circuit. And there's two things we want to know. We want to know the impedance of the circuit, which is the resistance of the circuit. And we want to know the power factor, This is called a power factor. It's got a name. The phase difference, okay? And that's important because what does that tell you? What does the power factor tell you?
Whether you're cooking or not,
Huh?
whether you're cooking or
Yeah,
not,
whether you're cooking or not. When are you cooking?
when P is 0,
Yep. And when are you not cooking?
when P is -5 or 2 or 5 or 2.
Yeah. So if it's plus or minus 90 degrees, you're not cooking. If it's 0 degrees, you're cooking. All right?
What if it's like 5 or 4?
You're still cooking, but you're not cooking efficiently. There you go. All right. So do we understand that? So now I'm going to show you various circuits, 4 or 5 circuits, very simple circuits, because all you paid was $500. So we'll show you very simple circuits, and we'll give you Z and phi for those guys. Okay? All right, so let's do it. So here's the simplest one. Okay? So here's a pure resistor connected to an AC source. Okay? And we're not even going to derive anything. So here's the AC source. The current is V max over R. So Z is R for this circuit. And I'm going to keep writing this. Our Z is R. And what is phi for this circuit? Hmm? So there's the expression. So you always compare it to this expression, Vmax sine omega t, I equal to I max. Okay, so compare this to that, and you can see that phi is 0. Okay? So this fellow is cooking. Okay? So you connect an AC source to a pure resistor, and it's delivering power to a maximum extent to the load. So that resistance could be a bulb, and the bulb will light up. Okay? The resistance is your toaster, and the toaster works. Okay? You'll see in a second, you connect an AC source to a pure capacitor, nothing is cooking. All right? So here's our first simple circuit. We found those two things that we wanted to find. All right, now we'll introduce a couple more ideas. Okay. Again, so all these expressions are similar to the expressions for DC circuits. Power, so when you had a DC circuit like this, the power dissipated in the load could be calculated in one of 3 ways: I square R, V square over R, and V times I. Okay, so we have connected an AC source. Let's say we have connected an AC source to this resistor. This could be a light bulb, and the power dissipated is I square R. I is that. I square is that times R. Okay, you can see that this is sine square theta. The instantaneous power is varying like this. What is the frequency you get out of the wall? What is the frequency of the signal that you're getting out of the wall? You should know.
0.
It's an AC source. You're getting a 60 hertz signal, 60 cycles per second. Okay? So look at this. Let me turn this light on. Because Courtney won't understand this. If this light turned on, it's being fed by an AC signal, and look at this. So that's one cycle. You have 60 of those. This is the brightness of the bulb. The bulb is blinking on and off 120 times a second. Do you ever see it blinking? So what's going on? Maybe I lied to you.
Is it going so fast we can't see it?
And that's right. So if it blinks on more than 30 times a second, then it appears continuous. So that when you're watching TV, it's a set of diagrams being drawn, still diagrams. You draw more than 30 of those a second, you see continuous motion. Okay, so that's what's going on. All right, so now here's the important thing. So this thing is blinking on 120 times a second. Okay, you can't perceive it, so all you care for is average power. Okay, so to get the average power, what you can do is, so see, this is a function of time. The period is t. T is the period. And so to get average power, all you do is you take the power as a function of time, integrate it with respect to t over one period. Okay? And here's what you get. So average of sine square theta over one period is 1/2. Okay? So you get I max square r over 2. Now this guy is a pain in the neck. Okay, you don't want to carry him around. You want the expression to look like this for the power. So we'll define a new quantity IRMS, which will be I max over root 2. Okay, IRMS. And the name comes from the following. It's the square root of the average of the square of the current. Root mean square. Okay? So that's where the name comes from. All right. So, like I said, it's IRMS, or similarly you can define VRMS. VRMS will be V max over root 2. Okay, so the 120 volts that you get out of the socket, that's the RMS voltage. The amplitude of the voltage is VRMS times root 2, which is about 170 volts. Okay. All right. Now, I hope you're following this. I'm not going too fast, am I? Okay. So let me ask you a question. So here's a vector. What is the y component of this vector?
A times sine theta?
A times sine theta. All right, see the voltage is V sine of an angle. The current is amplitude of the current sine of an angle. Okay, so the instantaneous value is the y component of a vector. You can think of that. Okay, so we will define something called a phasor. Okay, so here is the amplitude of the current, here is the amplitude of the voltage, and here is the angle, omega t. And you see as t increases, this vector is rotating counterclockwise. And what is the instantaneous value? It's the y component. Okay, the reason we introduce this is because when you're analyzing complicated circuits, and you'll see one little example of this, again, you'll see that instead of having to solve differential equations, instead of having to solve complicated differential equations, if you understand phasor diagrams, then you can figure out I and Z, phi and Z easily.
And trigonometry?
With trigonometry. With actually just adding vectors. Mm-hmm. Okay, so, and that's always good. Okay, if we can learn little tricks to simplify our lives, we'll learn them. Okay, all right, so that's the phasor diagram. So all you do is start off with a phasor, make it rotate counterclockwise. You want the instantaneous current, you just take the y component of that. Okay, so the instantaneous value for the resistor, for the voltage across the resistor is that, and there's the current. And it's a y component of those phasor diagrams, those phasors. Okay, so phasor rotates counterclockwise at the same frequency as that associated with the variable. All right, so what is it that we are looking for? We're looking for Z and phi of a circuit. Okay, and we're doing simple circuits. We just got done with attaching a resistor to a AC source. Now we're going to attach an inductor to an AC source. Do you guys remember any properties of the inductor?
Fights against changes in current.
Very good. It doesn't like changes in current. And here you are, you're connecting an AC current to it, which is changing all the time. This fellow is not happy. What else do you know about the inductor?
It holds power, it retains power, it charges,
It stores energy.
stores energy.
Yep, okay, very good. Okay, how does it store energy?
Through a magnetic field.
Very good. All right. So really what's happening in a pure inductive circuit, in one cycle you're storing energy and then it gives right back. So if I have an ideal inductor, no cooking is going on. I'm giving Jacob $5 and then he gives it right back. I give Jacob $5 and he gives it right back. Neither one of us is getting richer. Okay. All right. So, how, again, you'll use all the bags and the tricks to analyze circuits. So here's the circuit. We hooked this. It's a complete circuit, and Mr. Kirchhoff tells us that the sum of the voltages across all elements around a closed loop is 0. So we're going to go from here to there. That's V max sine omega t. And then you go from here to there. As current is increasing, if current is increasing, this becomes positive. The voltage across that is minus L di by dt. Okay. So the behavior of this circuit is described by this differential equation. Okay. What are you interested in? You are interested in I as a function of time. See, for this voltage, there's the current. All right, so I'll write this in the general form. IT is V max over Z sine omega t minus phi. So for a given circuit, we are interested in Z and phi. What is Z for this circuit? Omega L. So Z, the resistance of this circuit, of this element, is omega L. What is phi? Plus pi by 2, right? All right, so you've learned something new. Okay. What was Z for this guy? Again, I hope it's not too busy. Well, Z for this guy was R. Z for this guy is omega L. It's dependent on the frequency. So here's a first element you've seen whose impedance, whose resistance depends on the frequency. for a pure resistor, you can connect any frequency and the resistance remains constant. It's not frequency dependent. Okay, and this makes sense. Higher the frequency, the current is changing more often, and this guy sure as hell doesn't like it. Okay, so the frequency is linearly dependent on frequency. Higher the frequency, higher the resistance. The louder he'll squawk. Okay.
It's still not actually really doing anything though, right? Because it can't like cook,
Right, it's not cooking. Yeah.
but there is still a current.
Yeah, there's still a current. So this guy is used, well, so what does he do in life? He smooths out currents. So whenever you want to do that in some part of the circuit, that's when, okay. You want to store what was the capacitor doing in your flash camera circuit?
Storing it so it can produce electricity.
There you go. So that was the job of the capacitor. He couldn't cook, but he could hold on to the money and deliver it fast. It's like, you have money in real estate. You can't liquidate it that fast. You got to have cash in the bank if you want money fast. So that's the job of the capacitor. Okay? All right. So they all have their function in life. Okay? All right. So again, we want to look at the phasor diagram. Okay? So you see, here's another thing you want to notice about this. So we found the two things that we wanted to find about this circuit. Okay, notice something else strange. Oops. Okay, now let me point out. So here was the resistor. Okay, so let's look at the diagram. So this is the AC source connected to the resistor. As the voltage is increasing, you see the current is increasing in lockstep. Okay, the voltage decreases, the current decreases in the resistor. This guy is, here it's not happening. See, as the voltage is increasing, the current in the inductor, there's a delay in response. I tell my son to do something now, he does it 10 minutes later. That's what's going on here. Okay? So the voltage is increasing, the current delays, and then the voltage is decreasing, and then 10 minutes later it'll decrease. Okay, so the response is not immediate. All right, so the two things we have to know is, so again, the resistance is omega L, impedance is omega L, and again, this is given a special name. It's the inductive impedance, it's called XL. So R to Z to XL. Okay, that's the special name. And it's dependent on the frequency. Okay. We'll do the phasor diagram. Here is the voltage phasor. And you see the current is 90 degrees behind. So here is the voltage phasor, and here is the current, 90 degrees behind, and then you rotate this. And you want the instantaneous value, just take the y component of that, those vectors. Okay. All right, so we've done R, we've done L, and now we'll do C. Okay? So there we go. We're connecting a AC source to capacitor. What do you know about a capacitor?
Stores energy like using electric fields, right?
Very good, very good. Okay. Again, you'll see that it doesn't cook. Okay. So there's the AC source, there's the capacitor. Okay, you guys might remember capacitance is defined as Q over V. So Q is C times V. Okay, so Q, the charge on the capacitor is the instantaneous voltage times the capacitance. There is the instantaneous voltage times the capacitance. And what you are interested in is the current in the circuit. Okay, the current is dq by dt, so it's dq by dt. You get omega c cosine omega t, and so we want to express it as a sine. So cosine omega t is sine omega t plus pi by 2. All right. All right, so I'm going to write IT as V max over 1 minus omega c sine omega t plus pi by 2. And we're going to compare this to the general expression IT equal to V max over Z sine omega t minus phi, the defining equation. So what is omega? What is Z for this circuit?
One over omega c.
Very good. Okay, so the resistance of a capacitor, the impedance of a capacitor, also is frequency dependent, and it's inversely dependent on frequency. Higher the frequency, lower the impedance. Okay? And it's given a special name. It's called XC. Okay? And the other thing we wanted to know was the phase difference. What is the phase? Very good. Negative pi over 2. Again, this guy doesn't cook. I give him $5. He gives it right back. $5, $5. But, the stored energy you can use for many things. You can jumpstart hearts. You can take flash camera pictures. Anything else you can think of?
Heart, heart.
Yeah, heart defibrillator. You can fire lasers for fusion reactors. Okay? So you can do all kinds of stuff. Nowadays, a lot of the sports cars. You guys have heard of regenerative braking. You can charge supercapacitors. If you have a $250,000 car, electric car, you can do that kind of stuff. And then take off like a rocket from a red light. Okay? So you can do all kinds of stuff. All right, so you can see that here's the voltage, and the current is ahead of the voltage. Okay, again, the current is not in lockstep with the voltage. Here's the voltage, and the current is like that. So when the voltage is increasing, the current is decreasing. When the current is, the current is decreasing partly, and the voltage is decreasing, and the current is increasing. Okay, so they're not in lockstep. They're 90 degrees out of phase. Okay, so here's the phasor diagram. Here's the voltage phase. The current vector is phasor is ahead, 90 degrees, and this phasor rotates that way. Okay, the impedance is 1 over omega c. As the frequency increases, the impedance decreases. All right, so we've done resistors, we've done capacitors, and we've done inductors independently. Now we'll do the next complicated thing. We'll combine them together. Okay. Now there's many ways of combining them. You could here's a parallel combination, and there are many others. Okay, so there's many ways of combining them. Okay, but this is what we'll consider, because this is the most commonly used configuration. Okay, this is the configuration used in tuning circuits, which we have trillions of. Okay. So we'll consider that. All right, so again, you could use Kirchhoff's rule, take the loop rule, and set up a differential equation, and the differential equation will be a second order differential equation. Okay? All right, we don't want to deal with that. So here's your voltage, here's the current. Okay? What is it that we want to find?
The impedance and V.
Yep. All right. So I'll show you. So remember the phasor diagram. Why did we invent the phasor diagram? Because Jacob was too lazy to solve differential equations, and so we wanted to make his life easy. All right. All right, so here's the current amplitude. For the resistance, the voltage and current are in phase. The capacitor, the current was 90 degrees ahead of the voltage across the capacitor. The voltage across the inductor was 90 degrees ahead of the current. So this is the, let's say the current phasor is here, the voltage across the inductor is there, the voltage across the capacitor is here, the voltage across the resistor is here. The net voltage is the vector sum of all these guys. There is the voltage phasor across the RLC circuit. And now we'll rotate this counterclockwise. There's the phase angle that you wanted. Okay. This value, like in a DC circuit, V is equal to I times R. Okay, so V max will be I max times the impedance. So this will be I max times R impedance. This will be V I max times R. This will be I max times XC. This will be I max times XL. Okay, so V max is VR plus VL minus VC. We'll apply the Pythagorean theorem. V max is VR square plus VL minus VC square. I max, and there are the expressions. I max is common, we'll pull it out, and this is Z. So this is equal to I max times Z. So the impedance of an RLC series circuit is that. Okay. And then the phase angle is tan inverse of, well, this is phi, and so phi is tan inverse of XL minus XC over R. Okay, so those are the two things you wanted to know about the circuit, and they're there. Yeah. And this is for a RLC series circuit. Okay. There were many other combinations, and so that's a little more complicated to find, and so that's why we're not doing it. Okay. All right, so if you have a purely resistive circuit, there is the impedance, and so like I said, these two guys are so important that they've even made a table for you guys. Okay? And so for a purely resistive circuit, there's R and there's Z and phi. For a purely capacitive circuit, phi is minus 90 degrees. For a purely inductive circuit, plus 90 degrees. And if you have a combination of a resistor and a capacitor, it'll be somewhere between 0 and minus 90 and 0. If you have a combination of these two, it'll be between 0 and 90. For these three in series, if this guy is greater, then it'll be between 0 and 90, and if XC is greater, then it'll be negative, and so on, okay? All right, now we'll come to the power factor. All right, so what we're talking is the following. We have an AC source, so that's, and your black box is plugged to the AC source, okay? And the question is, are you cooking? Okay? All right, so the power delivered to the load is V times I. There is I, and there is V. Okay? And of course, this is the instantaneous power. And you can calculate the average power. How do you calculate the average power again? 1 over T, that's the period. Instantaneous power, 0 to T dt. Okay, do that integral for this guy. Okay, so there's the function of, and what you'll find is there's I max, V max over 2 cosine phi. So now you see, if phi is pi or plus or minus pi by 2, this is 0. The average power delivered to the black box will be zip. When is the average maximum power delivered to this black box?
Phi is 0.
When phi is 0. Let's say this is Palm Coast or DeLand or whatever, and this is FPL. If phi for Palm Coast or Deltona is pi by 2, everybody's in the dark there. Okay. All right, so now okay, so here is a power company. Power to your city is coming via transmission lines. Okay. These transmission lines have an inductance associated with them, L associated with them. Okay. So they have an inductance associated with them. So phi is between 0 and 90 degrees. Let's say it's 45 degrees. You're not delivering power most efficiently. So what you have to do? What you do is you add capacitors such that this becomes 0 and phi becomes 0. So you add capacitances, banks of capacitances in front of the city, so this becomes 0, so phi is 0. And that's what these guys are outside your city. Okay. You guys have seen this stuff? Outside, near every city you'll have these guys. Okay. So power capacitors are used to balance the impedance effect of the effective inductance of transmission lines. So what is it that you're trying to do? You're trying to make phi 0 such that maximum power is delivered to the city. All right, so there's the power factor. And so now you see why you needed to know phi. All right, so here's the amplitude of the current, the RMS value of the current, VRMS divided by Z. When is the current maximum? When the denominator is minimum. These guys are frequency dependent, so you can make this 0, and that's when IRMS will be maximum. So when this is 0, that corresponds to this frequency. So when power is delivered at this frequency, then the current amplitude is maximum. So, okay. And of course, the amplitude of the current will depend on the resistance. Okay. All right, so if you want to deliver power, so power is being delivered at 60 hertz to us. Okay, so you're making sure that this bank of capacitor, it's XC minus XL equal to 0. That is omega C minus 1 over omega C minus 1 omega L equals 0. This is at 60 hertz. Omega is 2 pi F. F is 60 hertz. Okay, so your capacitors are such that you want that to be 0. So here's an AC source. An RLC circuit. Okay. So this is your load, this is your cooker, and this is the AC source. Okay. And what this diagram is showing you is the following. So at this frequency, at omega naught, the amplitude of the current I max is V max over R square plus XL minus XC square. Okay, at this frequency, this guy is 0. That's the resonant frequency. And current is maximum, and maximum power is being delivered. Okay, and the quality factor shows you as you move away from that frequency, how fast does the power delivered fall off. Okay, and this is important for tuning circuits because if instead of this source, it's an electromagnetic wave that is coming, for a particular frequency, you have the strongest signal, and any nearby frequency doesn't give you much power delivered. If that is true, then you can have a station here, you can have a station at this frequency, and so on. So if the power factor, okay, if the quality factor of your tuning circuit is good, then you can have many more frequencies trying to talk to you. Okay?
And the finer the knob,
Mm-hmm.
means the more frequency, the more stations that you can have. That's because you're
No, the quality factor, the sharper the curve, the more you can have.
sharper.
Yeah. What you're doing by tuning is choosing which frequency you want to.
Oh,
Okay. So here's the tuning that you're doing. All right, so if the quality factor of this is sharp, then you can have a close by frequency and so on. So that's what those HD radios do, which never caught on. Your FM radio, what frequencies can it catch? You guys know the frequencies you listen to? You guys listen to radios? Every 10 years, you got to invent new technology. All right, 105.5 megahertz, 105.3 megahertz, 105.7. So every 0.2 megahertz, okay, you have to, so every 0.2 megahertz is where the frequencies is. The high definition radios, you can have frequencies at 1.4 megahertz and so on. So at half the thing. Okay, so for high, the quality of the circuit is, the peak is half as wide. Okay, the peak is sharper. And you see the width of the peak, smaller the R, the smaller the width. Okay. The problem with having small currents, small R, is if you pass too much current, things will burn. Okay. All right, so so here's a tuning circuit. Okay, instead of the city, now this is your tuning circuit. Instead of the source, we have an electromagnetic wave. and that is being caught by this dipole antenna. Okay, so this is your power source. This is your net to catch the fish. Okay, and this guy will deliver maximum power to your circuit at a specific frequency, at a frequency that corresponds to XL equal to XC, 1 over omega LC. Okay? And that frequency, you're delivering maximum power to this guy. And that's how you tune your circuits. Okay. All right, so here's an important application of Faraday's law. Okay, so you can step up and step down voltages for AC voltages. You can't do this for DC. If you wanted to do for DC, you would have to convert it to AC and then back to DC. Okay? All right, so here is a transformer. You attach an AC source, and here's the output source. Okay, so this will produce a magnetic field which is changing, and this magnetic field is coupled through this soft iron magnetic material to this secondary coil, and the voltage across the secondary coil is N2 over N1 times V1. N2 is the number of turns here, N1 is the number of turns here. Okay, so if N2 is 1,000 times greater than that, the output voltage is 1,000 times greater than the input voltage. Okay. Okay. So that's what's being done. Oops, where is that guy? Yeah, so here, see, this power plant is producing electricity at 12 kilovolts. Transmission happens at 800,000 volts. In China, they're doing it over 1 million volts. You can't go arbitrarily really high. Higher the voltage, there's leakage, sparks flying in. So, but anyway, higher the voltage you transmit at, lower your power losses. Do you guys know how much power is lost in getting from here to there? About 6%. Okay, so somebody sends $100 and $94 get to your house. Of course, you want $100 to get to your house, but right now $94 are getting to your house. Okay. All right. Hold up your laptop. What does that thing work on? DC current. Okay, you can plug it in to the wall. So what you're getting out of there is AC voltage, but that thing works on DC voltage. Okay, so how do we do that? Okay, so now we'll learn this. Okay, so this is a diode, and it's sort of a gate. If this end is positive and this end is negative, this end is at a positive voltage and that end it'll let a current pass through. Okay. If this end is connected to the negative terminal of a battery and this end is connected to a positive terminal of a battery, no current flows through. So it's a one-way gate. It can only let current flow through this way. So it lets current flow this way. It doesn't let current flow this way. Okay. Whereas a resistor, it doesn't care. It'll let current flow either way. So this beast is different. Okay. All right. So what we're going to do is we're going to connect an AC source to this guy. An AC source applies an alternating voltage. And so this guy only lets currents go through this way. Every time this guy tries to pass when this is negative and this guy is positive and tries to pass a current through like that, he'll stop it. So this guy only lets half current pass through during half the cycle. Okay, and if you stick a voltmeter there, this is what you'll see. But you're leaving half the money on the table. For every $100, you left $50 on the table. That's not good. So you're upset. So here's what you do. Buy 4 of these guys. So when this guy is, so let's see, when this guy is positive, current will go through here, go through here. How about the other half of the cycle? When this guy is positive, current will go through here. Okay, so now with 4 diodes, you feed a signal like this. And this, what you see out here is this output. So you picked up all $100. But her laptop is very finicky. Doesn't like this guy. What he wants is a flat 12 volts. Okay, so you got to smooth this guy out. So what you do is put a capacitor. And now the voltage across this is that. All right, hold your brick up. No, your brick.
My phone?
No, your brick. That's the brick, he knows.
Oh.
That, yeah, so that's what's in here. So you guys, your charger and stuff like that, for iPhone charger and all, that's what that is. So it's converting the AC signal into a DC signal, okay? And that's what that is. All right.